We'll start in a minute or so.
Yes, sir, sure.
Okay, so let us get started. Welcome to the session 8 of the problem solving sessions in this course, Parameterized Algorithms 2024. So today we are going to look at the assignment questions of week 8, not from this year's offering, but from previous year's offering. So there are 4 questions only. So I suspect that we will finish uh, in at most 1.5 hours. So this is question 1 for you. So I think everybody is aware of the definition of set cover. So you are given a set of elements, and this is called the universe. And from the universe, there are certain subsets which are given to you. The objective is to pick some of these subsets from the family. So this set of subsets is called a family. So from the family, you want to pick some of these sets, which is called a subfamily, such that their union together is the universe. So ideally, you would like to minimize the number of sets that you would pick to cover the universe. So to do so, one can use the dynamic programming approach and obtain this table. The first thing is to understand how this table has been formed and what are the meanings of these table entries. So the table is denoted by pi, and on the uh, on the columns it has the subsets, and in the rows it has the uh, uh, some indices. So what these indices means, so you have to understand. Okay, and then we have to compute this entry, which is corresponding to x equals abc and j equals 4. So first is to understand what this entry means. So I'll write it down. So before that, are there any doubts about what is the question asking?
No, no, question is clear.
Okay.
Yeah. So I could understand the meaning of this pi xj is that how many minimum number of the sets are required from S1 to Sj to cover the vertex x, like to cover x. Like say, if we consider the entry corresponding to the row number 2 and say column corresponding to a comma b, then it says that the entry is 1. So it means that we require the set number 1 to cover minimum number of, I mean the minimum number of the sets required. Probably I don't understand whether it's a count or the set number. So
Okay, it's count only.
okay. So if it is count, then it shows that only one set is required to cover a comma p, but we do not know that which set is required out of these four.
Yes, yes. So you have already deciphered the meaning. This is very nice. So yeah, so the indices are corresponding to uh, the sets. So there are 4 sets. J equals to 0 means you are not allowed to take anything. J equals to 1 means you are allowed to take only set 1. J equals to 2 means you are allowed to take sets from set 1, S1 and S2, and so on. So at most you can take all the sets in the family. So there are 4 sets. That's why J goes from 0 to 4. So I'll write down what pi xj means. But whatever you said is exactly what I'm going to write down. So it is the minimum number of sets. So with hash, I say, okay, I'll just say minimum number. So minimum number of sets. Okay. From, so you are allowed to take only sets till Sj, from S1 through Sj, required to cover X. So what is X? X is a subset. So what is X? X is a subset of the universe. So you are saying that, okay, I am not insisting on covering the entire universe, but I insist that a part of the universe, which is X, should be covered. But I'm also insisting that you are not allowed to take any of the sets, but you are allowed to take only a subset of the sets. Then what is the best you can do? So that is the meaning of the table entries. All right. So what does the last entry mean? So what is the English translation corresponding to the last entry?
So that would be the minimum number of the sets required from S1 to S4 and required to cover A comma B comma C.
Okay. So that is nothing but equivalent to finding the minimum set cover for the universe.
Yes.
So this is nothing but the minimum set cover. Okay. So now one can do all this dynamic programming business, or one can simply be clever and ask that how many sets are sufficient to cover the universe.
Yes, so and then for the AVC, we have got say 2 raised to the power 3. I mean, that is so basically, I mean, from the AVC, I will find all the subsets whose length is, I mean, 2. Like in this case, so if we are in general, say if we try to find the entry corresponding to the, say if the universe comprises of n number of the elements, then I would try to look for the entries having n minus 1 number of the elements. Like in this case, a comma b, a comma c, and then b comma c. And
Okay.
for the a comma b, I will find the minimum entry out of in for the 3 things, and then I will look for the minimum entry for the remaining one element. Like say if I choose the minimum value for a comma b, then I will look for the minimum value of c. So
Mm-hmm.
then probably we can yeah, find something here.
Okay.
Yes, yes.
So you have suggested a recurrence. You said that, okay, so what are the sub problems? So you said, okay, I will consider some subset of the universe, and preferably the subset has exactly one less number of elements than the universe. And then I try to solve this problem for that subset. And then I will have only one element to cover. Then I will add additionally one more, at most one more subset, and that will be a set covered. So that is
Yes.
valid only. But even without doing a recurrence, if you just ask that, just look at the input, and to cover ABC, how many sets you should pick. So how about just looking at the question and answering?
Okay, so by looking at the question, if I want to cover ABC, so I will look towards its left. And to cover BC, I require 2 items, definitely. And then only A is remaining. And then to cover A, I require 1. So 2 plus 1 is equal to 3. I would be requiring 3. But then I can see from the question that S1 and S4, only 2 subsets are sufficient to cover ABC. But yeah. But then here, so if I take, oh yes, but then if I take the value of AB as 1, and the minimum value of A comma B is 1, and the minimum value of C is 1, so yes, so two sets are sufficient. Yeah.
Yes, 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 yes. So taking S1 and S4 covers A, B, C, the entire universe. So this gives us sufficient confidence that the answer is 2. But that is not the purpose of the question. The purpose of the question is sort of to know what is the recurrence and then use the recurrence and then look up certain values and then answer. But of course, we will, for the purpose of verification, we will keep in mind that the answer must be 2. Okay, so now I will write the recurrence. So, so think of it this way. So what you said is also correct. But so when we are going to write the recurrence for phi x comma j, so we have to say that, okay, I am willing to cover the partial universe X with the sets from 1 to j. But to solve this problem, what smaller subproblems can I look at and answer? So we are at some position. So we are interested in obtaining these entries. Then which entries in the table we should look up to sort of calculate this entry? So first thing is how to break X, okay, or how to break J, whichever way. So yeah, so now uh, we'll try to see what happens with the second parameter. So second parameter is imposing the condition that you are not allowed to take anything other than these sets S1 through Sj. So now in the minimum set cover for X, two things are possible. One of two things are possible. Either Sj is part of the minimum set cover that covers X, or it is not there. So there are only two possibilities. So if you have taken Sj to cover uh, some of the elements of X, then you are left with covering X minus Sj. Okay, so let me draw this. So let us say this is X, and let us say Sj is, I'll take another color. Sj is a set that covers some of the elements of X. So these elements of X are covered. If you take Sj in the set cover for X, then you are remaining, you are left with covering this remaining part of X, that is X minus Sj. So the two possibilities, you either take Sj or you don't take Sj. So if you take Sj, then you have to cover the remaining part, but then you are not allowed to take Sj anymore. So you are allowed to take any of the remaining j minus 1 uh, sets. But you have already taken Sj, so whatever you get from this table entry plus 1, because you have already taken Sj. So the count of how many sets you have taken increases by 1. This is one possibility. When you have definitely taken Sj to cover X. The other possibility is that you have definitely not taken Sj. So if you have not taken Sj, then you are forced to cover X using the elements from 1 using the sets from 1 to j minus 1. So this is the scenario corresponding to not taking Sj. So are there any more possibilities?
Um, yes, so the first possibility is okay, and the second one is okay, and we take the minimum out of these two. It's fine. Yes, and by not considering J, but I don't understand the interpretation of the second one. That so we decided not to consider Sj. So
Yes.
then it becomes a minimum of x comma j minus 1, and these, I mean, both the values must have already been calculated, since every time we are taking j minus 1 as the second argument. It makes sense. Yeah, it's clear. I cannot think of any other possibility.
Yes, yes, yes. So we are sort of filling this table bottom up. So this is the recurrence. This is the recurrence, but at some point the recurrence will bottom out. That means at some point it will hit what is called the base case. So now we have to also define that what are the base cases.
So these cases must have been given in the first row or the first column, I guess.
Yes, yes, yes. That is true. So the first row is corresponding to j equals to 0. Yes. So if you set take some s and 0, so that is saying that what is the minimum number of sets you require to cover s by not taking any sets at all. So 0 sets are allowed to be taken, but your task is to cover some part of the universe, which is s. So that is impossible. That is not even possible. So that's why we'll say this is infinity. That means the number of sets required with this condition to cover S is not even possible. Okay. So if
So, yeah, will this be S or X?
you
Or
can, yeah, I mean, you can make it X also. That is also fine.
yes.
So that is the base case. So you know that in the first row, you are not able to cover uh, non-empty sets using nothing. That is not possible. That's why the first row is entirely infinity, but not this entry. So why is this entry 0?
So this entry is 0 because we are not considering any set, and neither we need to cover anything. I mean,
Yes, yes, yes.
we need
So
not to
it
cover.
is, yeah. So we can cover nothing using nothing. So that is why to cover an empty set, 0 number of elements are sufficient. So the other base case is what you said is corresponding to this column, the first column. So the first column is corresponding to empty set. So you are not intending to cover anything. So and then you have whatever budget you have, it does not matter. So this because you are not intending to cover anything. So none of the sets are necessary. So that is why the first column is 0. Is that fine?
Yes, yes.
Okay. So now with this recurrence, you know that, okay, you have defined the first row and the first column, and now you are going to go row wise. And this recurrence is such that to compute xj, the dependence is only on the previous row. So that's why the previous row entries are already computed. So we can compute this entry. So now we have to ask that, uh, okay, so yeah, so now so we'll we have to make some more space. Let me write down. Maybe here itself I'll make some space. So I want to write this entry. I'll take a different color. Blue will be better or red will be better. So I'm interested in this entry corresponding to ABC and 4. Okay. So the question arises is whether you are going to take S4 or not. That is the question you have. Okay. So if you take S4, so what is S4? Let us look at S4. Uh,
S4 is C.
yes. So S4 is C. So there are two things we have to compute, that S4 is taken or not taken. That's all you have to compute. I want to see everything in the same round. Now everything is visible. So minimum of two things. One is when S4 is taken. So when C is taken, then we are left with covering AB. So pi of AB, and now you are allowed to take the remaining 3. But you have already taken S4. The other thing is that you have not taken S4. So then you have to cover the same set, but this time you are not allowed to take S4. Okay. So now these two entries we can look up from the table. So AB3.
Yes, this value is 1.
Yes. So 1 plus 1. So this part is 1. And the other one, sorry, this part is 1 plus 1, 2.
Yes,
And this is ABC, comma 3.
independent.
So that is ABC, comma 3. So it is saying that using S1, S2, S3 only, ABC cannot be covered. That is what it's saying. Fine. So this is infinity. So this is 2. The minimum of these two is 2. So that means our answer is 2. So what it means is that if you take S4, that is C, and if you intend to cover AB with the first three sets only, then you will definitely take AB. So S1 will be taken. So it is not only, so slightly modifying this table, one can not only tell the minimum number of sets required to cover X, but also output the sets which are in the minimum set cover. Okay. So this is our answer.
But I have a doubt here. So it's okay that this strategy works, but then I mean, for a problem in general, we would be having exponentially large number of the columns in the table.
Yes, yes.
So yeah, so even
So
though
the,
this, yeah,
yeah, go ahead.
so even though this DP is generating a solution, but then that won't be a right strategy for solving this problem in general.
You are right. So the recurrence is such that the running time is sort of exponentially dependent on the number of elements in the universe. So if there are any n elements in the universe, then you have 2 to the power n columns because there are 2 to the power n possible subsets, and the number of uh, rows is the number of families. So let us say there are m families. So I'll write it down. So if there are, in general, if there are m families and there are n elements in the universe, then the running time is definitely 2 to the power n times m into whatever is the cost of computing one entry. So many entries are in the table for sure. Now the cost of computing an entry, so there is some addition. Is one lookup, two lookup, there is some addition, and then there is one comparison, which is because of finding the minimum. So there is some constant amount of work required to sort of compute one entry. And the number of entries itself is 2 to the n into m, where n is the number of elements in the universe and m is the number of families. So the running time is 2 to the n into n. That is true. Uh, yes.
Yes, yes, yeah,
But set cover itself is an NP-hard problem, so we do not expect polynomial running time also.
yes.
Uh, but if the number of elements in the universe is not too large, then this makes sense. Otherwise, not.
Yes, yes. And this reminds me of something, I mean, like a threshold kind of a thing or a tipping point kind of a thing that I mean, beyond that tipping point, the problem becomes really difficult. And then probably in that case, we can use the techniques introduced in this course, SPT or the formulation, if possible. Is it like,
Correct, 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 correct. I agree with you.
okay,
So yeah, so this is just demonstrating that set cover can be sort of tackled with DP. This is just showing that there is a nice way to sort of uh, show an optimal substructure property which can be exploited to show a recurrence. But then, of course, your doubt is valid that running time is not within polynomial limits. So there is not much we can do about it.
so I have a related query here that do we have, I mean, some reference available wherein I can look and find that whether, I mean, an approximate solution of this set cover has been obtained by some strategy or not. Like say, whether the FPT is possible for this, whether the kernelization is possible for this, or whether do we have an approximation algorithm for this. So do we have some reference available to quickly find, uh, I mean, the current situation or the state of the art situations of these problems.
So as far as approximation is concerned, the greedy algorithm is a log n approximation where n is the number of elements in the universe. And it is known that better than log n approximation is not possible in polynomial time. That is the status on the uh, from the perspective of approximation. Whereas there are some set systems for which better approximations are possible, but in general, better than log n is not expected. So better than log n would imply p equals np. So better than log n approx for set cover in general would imply p equals np. So that is not expected. But then there are set systems for which better approximations are possible. For example, in geometry, if you have set systems uh, defined by geometric objects. For example, if you say that, look, I have certain set of disks. Uh, yes, unit disks, let us say, same sized disks. So there are, these are the sort of families corresponding to families, and there are points which are corresponding to the elements of the universe. Now, depending on uh, whether a point is contained within a family or a disk, uh, one will define the sets. So there are so many things. So if the set system is defined by this geometric setup, that this is one set. So whatever points are within this circle, that is your one set. So first thing is you number the points 1 through n, and then depending on which circle contains which indices of points, you define the family. So in that case, we can obtain a pitas, that what is the minimum number of circles required to cover all the points. For that, we can obtain a pitas, that is a polynomial time approximation scheme, which is an 1 plus epsilon approximation. That means it is at least, I mean, it is very close to optimal. That means it is at most 1 plus epsilon away from the optimal, where epsilon is a number that you can control. So this is a very special set system. There are some other special set systems for which log n is beaten. But for general set systems, log n is not expected to be beaten in terms of approximation. On the other hand, whether FPT, so the FPT literature, what it says, I have to check. Let me quickly look at the book and see. So this is discussed in which chapter? So there is a parameterized reduction from dominating set to set cover. So whatever is applicable to dominating set will apply. So it is, there is a result in the book which says set cover is W2 complete. So there is some hardness. So there are hardness hierarchies like W1, W2. So it is W2 complete along with dominating set and hitting set. So I do not know what it means. Uh, I think it must be discussed sometime in this course. Let me check whether it is discussed in the coming weeks. So there is a week on hardness and lower bounds. So week 12 talks about different reductions. So I think that going forward we might understand the so your question is, what is the reference to know more about set cover and its parameterized complexity?
Yes, yes, because in that Green book, that book on this parameterized algorithm, so they have not given a summary somewhere that, okay, so that these problems have been attempted using the FPT, and for these problems, FPT is not possible, and probably the kernelization could be the appropriate thing. So actually, I could not find some guidelines given that, okay, for such type of the problems, the kernelization
Mhm.
could be a better strategy, and for these problems, the FPT is a better
Okay,
one. Could find out if you can filter out some characteristics of the given problem. In that
all
sense.
right. Okay, okay, okay. So I will have to look more about on it. So with a quick search, I can see that in part 3 of the book, which is lower bounds, there is the first section on fixed parameter interactability. And within that section, there is a section called the W hierarchy. And there I could see that there is proposition 13.20 followed by theorem 13.21. These two are talking about the hardness of set covered.
Oh,
But more on it, I will look it up. But for now, you can look at chapter 13,
sure, sure. Yeah,
section on W hierarchy.
yes. Yeah, I read something about the W hierarchy thing, but then I totally forgot what the W used to be now.
Okay, okay. So we can
Yeah,
talk more about it. So, yeah, so next class or sometime when we have time, we
sure,
can talk about this hardness as well. I will
sure,
also take a look at it.
sure.
So, this is the end of this question. So, we have identified that the minimum set cover size for this instance of set cover is 2. Okay. All right. So, this is question number 2. Okay. So, I will define what is a Steiner tree. But you can look at the question, then you can read the question. By that time, I will define what is a Steiner tree for you. So let me give an example first. So I'll define with an example. So I give you a graph, and in this graph, uh, along with specifying the vertices and edges, I also mark certain vertices as special. Okay. So this is a special vertex, this is a special vertex, and this is a special vertex. So the special vertices are also sometimes called as terminals. So I'll use the word terminal uh, for these special vertices. So now the question is, uh, given this set of terminals, can I find a connected subgraph H of this? Let's say this graph is G. So can I find a connected subgraph H of G that contains all the terminals? Okay. So let us say that this graph is undirected for now. So can I find connected subgraph H of G containing all the terminals. So in this case, is it possible? So give me some subset of the edges such that it forms a connected subgraph and it includes all the terminals. So let me give you an example. So is the following uh, valid connected subgraphs? This edge I'm picking, this edge I'm picking, this edge. Okay, this is all. Okay.
So, um, I mean, so do we need to find the connected subgraphs and containing all the terminals? So even though all terminals have been connected here, but not all the vertices. So is this
Yes, yes.
necessary for all the vertices or only the
Only the, yes, only the
okay,
terminals and some certain other vertices that are necessary to ensure connectedness.
okay, and while maintaining the sum of the weights assigned to the edges as minimum to the extent possible.
Yes, yes, yes. So if I ask that, what is the minimum number of edges that you must pick so that we have a connected subgraph? Yeah, so let us ask that question that in this figure, so we have a graph, we have specified the terminals, and we have also shown a subgraph H. Then is this the minimum number of uh, edges that we could draw to ensure that all these three terminals are connected?
Yes, like in this case, it is true that it is a solution, and further it will also depend on the weights assigned to the edges. Like,
Weights
uh,
are equal, let us say.
okay, so if all I mean edges carry equal weights, so then I'll focus on the number of the edges. Then,
Yes, yes.
like in this case, one, two, three, four, five, six. Six edges have been considered, and I do not find a solution better than six edges while covering all the terminals. Yes, this is the solution. This is the solution.
Okay. So how about, so I am drawing some green edges.
Yes, so here we have, I mean, we have five edges, but then
Oh,
it
sorry,
is,
sorry, sorry. I will connect it that way. It is not
yes,
better. It is not okay. Okay, it is not better.
yes,
So,
again, it's six edges.
okay, it is also six. Fine. All right, fine. So, but this is a valid Steiner tree. Okay, so Steiner tree means tree that connects all these terminals. So now think of the weighted version. Now we are looking at the question. Now this is the question that we have. In this graph, we have weights on the edges, and there are three terminals K1, K2, and K3, and these weights are given. Okay. So now they have built a DP table. So we have to first understand the DP table and what are the entries corresponding to, and then we will ask how to compute this entry. Okay. So first I have to define for you that what is the recurrence and what is the meaning of this DP table.
Yes,
Uh,
but it is not, just, I mean, is clear from this table.
can you repeat what you said?
So I said that the meaning is not, I mean, immediately clear from this table itself. Right?
Yes, yes, yes. Yes. Okay. Yes. Oh, one more thing I should tell, that if the number of terminals in the STEINER tree problem is only two, so if there are only two terminals, let us say this terminal is not there, this terminal is missing, so there are only two terminals, then the minimum STEINER tree, is it equivalent to some known problem?
Uh, so yes, so then I can, so yeah, I can apply here DFS thing, or the we call, yeah, DFS thing, that how many minimum edges are required to traverse from the vertex to the other vertex.
That is also true, but DFS will give you a, a certain path between these two terminals,
Yes.
and that path you will output as the connected component, but that path is itself something between these two terminals.
Oh, so reachability problem, I mean, I can find that whether I can move, make a move from this vertex to the other vertex, the source, and so I can use the extras here to
Yes,
know.
yes, yes. Minimum shortest distance, I mean the shortest path. So if there are only two terminals, so then asking the STEINER tree question is equivalent to asking the shortest path question between two terminals. So Dijkstra will be applicable, yes.
Yes.
On the other hand, if all the uh, vertices in the graph were terminals, then also it reduces to some known problem, some
Minimum,
polynomial.
minimum spell.
Yes, 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 yes. So if you want to connect all the vertices such that there are no loops, of course, there is no incentive of having a loop unless, okay, so with the assumption that there are no negative weightages, then there is no incentive of having any loops. So finding the minimum spanning tree and finding the STEINER tree, minimum STEINER tree, are equivalent problems. Uh, yes, but in general, when the terminal number of terminals is not 2, is greater than 2 but less than n, then the problem is no more polynomial time solvable. Then it becomes NP hard. So although for equals to 2 and equals to n, we know that we can find polynomial time algorithms.
Yes.
Okay. So I will describe this recurrence. So T of T comma V. Okay. So you can understand the meaning. It says that the minimum possible weight of a STEINER tree for, so D is some subset. Let's look at the figure again. So D is some subset of the terminals. So the terminals are K1, K2, K3. So on the column side, or on the row side, you have all the subsets of the terminals. So if there are n terminals, then there are 2 to the power n rows. And V is one vertex which is outside of the terminals, which is a non-terminal. So how many non-terminals are there?
So there are four non-terminals here.
So corresponding to every non-terminal, you have one column.
Oh, I see.
And then the question is that what is the minimum possible weight of a STEINER tree when you are intending to make sure that this subset D of terminals along with this non-terminal, they are connected. So when I'm looking at this entry, this is corresponding to the question that you want to make sure that K3 and B are connected. So if you are willing to ensure that K3 and B are connected, then what should be the weight of the tree? So
Yes.
look at
So
this,
yeah,
K3
and B,
and B.
three
So
plus
how will
one.
you connect them? This is the way to go. 3
Yes.
plus 1 is 4. So that is the meaning of this thing. But also we have to understand that how to write the recurrence. Okay.
Yes.
Uh, so I'll write the recurrence. It is not it's not immediately clear that how one should write a recurrence in terms of smaller subproblems. But you can give it a
Yes.
thought.
Yeah. So, like say, so I can fill these values. So whether I can fill the terminal values or not. So for K1, I can immediately fill the values. And for the individual cases, I can immediately fill the values. And then once these values are ready, then for K1 comma K2, so if I want to find the minimum possible weights, I'm covering K1, K2, and then K.
Mhm.
So I'll have to look. I want to include K1, K2, and then A. So whether K1 comma A is there, and then K2 comma K2 comma A is directly there or not. So if it is directly there, then K1 comma A, K2 comma A, and plus K1 comma plus weight of K1 and K2 invert B. But if K2 comma A is not there, so I need to look into the other path that so how can I reach to the vertex K from K2? So how can I reach from the vertex K2? Yes. So I think that that can be done. That can be done in that way. Say if we are trying to compute say T of D comma B, then we will
Mhm.
look for um, yes. So then we will look for okay. Uh, yeah. So D minus I don't know. So D minus one terminal, uh, and
Yes,
then
yes, you are right. So D needs to be partitioned into some pieces, smaller pieces. That is the
okay,
first observation you have.
yeah,
And the other observation you have is that if there is uh, these kinds of entries, the entries corresponding to these three rows, they are nothing but shortest paths. So this entry is corresponding to connecting K3 with A. So you have to find the shortest path between K3 and A. So you look
yes.
at K3 and you look at A and then ask that what is the shortest path. Maybe this is the shortest path. Yes. So if D is only a single terminal, then reduces to the situation where the number of terminals is 2, and that is shortest path. And the other thing is to write D comma B in terms of smaller. So if you can sort of break D into two parts, D1 and D2, then we can write these entries corresponding to D1 and some value, D2 some value, and then we can try to see how to combine the merge these two things. So that is a whole thing. Uh, on the other hand, one question that might arise that what is the use of this additional vertex P? So we are making so many columns corresponding to each of these non-terminals. So the question is not related to non-terminals. The question is only concerned about connecting the terminals. That once the terminals are specified, the question is how will you connect the terminals, making sure that the connected subgraph has minimum weight. So in this figure, I can see that what is so in this figure, if you want to connect K1, K2, K3 alone, so you will take these three edges for sure. Now what will you do? So you might take this, and that is connected, or you might just take these two and that is also connected. So you can see that the question of non-terminals, or rather including a non-terminal in the STEINER tree question, is not immediately obvious.
So it is, I mean, required. Why so? Because if K1, K2, and K3 all are connected together,
Yes,
so then this problem can automatically be solved. So we require these. So the problem is difficult because I mean they are not connected with one another. So we require some intermediate vertices, and
that is true.
yeah,
That is true. So the thing is, you are right. So if you are asking the question that, so if there are no non-terminals at all, if all the vertices are terminals only, then that reduces to the minimum spanning tree that we have already seen. So the connectivity among the uh, terminals are not there fully. So there is some non-terminal via which you must traverse to ensure that the terminals get connected. So it is natural to ask that what is that non-terminal that will help us the most for ensuring that there is connectivity among the terminals. Okay. So now we have got a fairly good idea about how to go about writing this recurrence. So now we can write this recurrence. So let us say that this set of terminals D, which is given to us, we write it into, or we break it into two parts. So we write it as D equals to D1 union D2, two parts. But D1 and D2 are disjoint. So this is a disjoint partition of the terminals in D. Okay. And now we are going to write the recurrence in terms of this D1 and D2. So T of D1 we will write, comma some non-terminal. T of D2 we will write, comma some non-terminal. I don't know why. What? Okay. So let us say that the non-terminal is different from V. For now, we say it's W. So and then we are so what are these two subproblems for? So this subproblem is the original problem is that what is the minimum possible weight of a Steiner tree that connects D and V. Okay. So what is the minimum possible weight of a Steiner tree that ensures that D union V are connected? This is saying that what is the minimum possible weight of a Steiner tree that ensures that D1 and W are connected. This is saying that what is the minimum weight of a Steiner tree that ensures that D2 and W are connected. So if you take this Steiner tree and this Steiner tree and take the union of them, because of the presence of a common vertex, these two trees together will ensure that D1 and D2 gets connected.
Yes.
All right. But that is not sufficient. You have to also ensure that V is also connected. So this is saying that D along with V are in a connected component. This is saying that D1 and W are in a connected component, D2 and W are in another connected component. So taking the union of these two will ensure that D1, D2 and W are in a connected component. So that means D and W are in a connected component, but additionally you want to make sure that V is also in a connected component, in the same connected component. So you will additionally find the shortest path, which I will denote as DIST. Dist means distance, means shortest path between V and W. So these three things together, if you take, this will ensure that you have got a Steiner tree that connects D with V, but you do not know whether this is the minimum Steiner tree. This is definitely a tree. These three things together, if you take union, they make sure that there is a Steiner tree that ensures that D and V are inside the same connected component.
Yes, so we can take minimum out of these many possible values, but then the
Yes, yes,
possibilities of W would be pretty large because
yes,
yeah.
yes, yes. So W is over all non-terminals. So there are many subproblems you have to consider. So minimum is over all W. So W belongs to all non-terminals. So let us say VG implies a set of vertices and K denotes the set of terminals. So here also you can see that this set K is denoting the set of terminals. So all the non-terminals have to be taken into account, and all the possible partitions of D into D1 and D2 you have to take into account. Okay. So with these three things, now you have so many subproblems. So the minimum among them is going to give you the minimum weight Steiner tree. That is guaranteed because you have not left anything. Uh, uh, so you have not left anything out. So you have enumerated all possibilities for computing T of D comma V.
So I could not understand that what this K here is and what are we excluding? I mean, why are we excluding it?
So K is the set of terminals which is given to you.
Mhm. Yes, yes, yes.
So all so this recurrence is over two parameters. D is a set of terminals and V is a single non-terminal. So that is why we are saying W is one non-terminal. It could be even identical to V, but I am interested in all possibilities. So I'm saying that W will be over all non-terminals.
Yeah, but I have a related doubt here that getting the values of the D1 and D2 itself is same as the very first problem we solved today, set cover thing, I think. Or because slightly a variation of the set cover. I mean, how many different, so how to find the values of the D1 and D2 so that their union will come out to be D.
Okay, so you are saying that so in that in set cover we had uh, allowed sort of sets to overlap. Here we are saying that D1 and D2 do not overlap at all. Their intersection is empty. So, so for example, in this figure, D is uh, uh, the, so there are if there are k terminals, then there are 2 to the power k possible subsets of terminals. Now, when I am interested in, for example, computing this entry, in this case, my D is K1, K2, and K3. So now in how many ways, if you know that D is only 3 elements, then in how many ways can you partition D into two disjoint parts, D1 and D2? So that number is also, uh, so it is other way of asking is, so it is like, so if D consists of D elements and D1 consists of small d1 elements and d2 consists of small d2 elements, then in how many ways we can ensure that d is equal to d1 plus d2? So this is something that is combinatorially determinable.
Yes, yes.
So this is the simplest way of thinking about is the following. So you consider d points. Okay. So now you want to put a bar in one of the gaps. So we have lined up d points. So you want to put a bar that partitions the d points into two parts. Now, depending on where you have put the bar, you have found two partitions d1 and d2. For example, here there are how many points? 1, 2, 3, 4, 5, 6, 7, 8, 9 points. So if I put the bar here, so I can say that 4 points are to my left and 5 points are to my right. So 9 is 4 plus 5. So if I had put the bar here, I would say 9 is 2 plus 7. So how many possible positions of bar do you have?
Oh, yes. So this is the combination with the repetition problem kind of the thing. So say if I
Yes,
want
yes.
to distribute here, so n plus r minus 1 cr kind of the thing.
Correct, correct, correct. So this is something that we can compute combinatorially.
Yes, yes, yes.
So this is something that is going to depend on how many terminals are there. See, we have a table of terminal size, number of rows in the table is already 2 to the power k. So here also we will take some 2 to the power k cost so that we can afford to take. Anyway, we are not aiming for anything below 2 to the power k. So then this can be calculated. So one thing is you have to consider that permutations of these numbers also, because the terminals are all distinct. If the terminals were not distinct, we could do it uh, more simply, but here the terminals are distinct. But anyway, the point is not, the point is that the number of cases that you will have is not going to be more than 2 to the power k or something. It's going to be ordered 2 to the power k only. So that's a slight digression from our discussion, but the point is it is doable with 2 to
Mm,
the k possibilities.
yes, yes.
Uh, all right. So this is going to give you a Steiner tree, or rather, this is going to give you the minimum weight Steiner tree. But this Steiner tree will only be obtained only when this recursion bottoms out somewhere. So you have to also identify that what are the base cases of this recursion. Okay.
Yes. So yeah, yeah. So yes. So uh, even identifying base case is also not that easy here this time. Uh, but
So you are breaking down D. So when you break down initially in this example, D is 3 terminals corresponding to this entry. So if you break it down, then it will have D1 will have at most 2 terminals. D2 will also have at most 2 terminals. If you break that further also, then you are at the case when there is only one terminal and then there is no way to partition it further. So the one terminal case is your base case.
yes, so then we can go for the first row then.
Yes, yes, yes. So all this part is your base case. I'll take a different color. All these entries are part of the base case, and this is corresponding to finding the shortest path between the non-terminal and the one terminal. And that you have to do with Dijkstra's algorithm in n
Yes,
log n time. Yes, so that is the base case. But once you have the base case, then you can look up. Then you can start looking up. Then using this recurrence, you can start looking up values and fill all these other entries. Shortest path problem. So now we are interested in finding this entry. So this last entry, what does this entry correspond to?
which one?
So,
Okay, yes, so this corresponds to uh, covering K1 and K2 and K3, and by taking uh, K1, K2, K3, comma D. So
yes,
taking till D or only D?
only D.
Okay.
So K1, K2, K3 and D needs to be connected by some connected graph. That is the question, that what is the minimum possible weight you have to incur to ensure that D is connected with all these three things.
Mhm, mhm.
So one is we can do all this business, or we can just look at the figure and try to see that which all edges we should pick so that D, K1, K2 and K3 are connected. And then we can add the values of these edges, I mean weights of these edges, and then we can populate this answer. That is a shortcut. So we'll do the shortcut first, then we can do the recurrence.
Yes. So yeah, and K1, K2, K3, and then D. So yeah. And so I'll look for then K1 comma A base case, K2 B, K2, K3 C. That
Yeah,
is
so which all vertices you have picked?
uh, K1 comma A,
This one, this edge, okay.
yeah, and then K2 comma B, and then
Okay,
K3 comma C,
okay.
and then I would like to pick uh, yeah. So then I like to pick say AD and then DC.
AD and
And I said AD and DC, but that won't be connected, I guess. No, so yeah, uh, so uh, A1A and then A to D and then D to C. I mean, this would definitely be there. And so, I mean, but the structure is like this that I'll have to move from C to D as well.
yeah, so this is probably the best you can do. You have to
Yeah,
ensure connectivity also.
yeah.
So
Here also I need to connect, say, C and B also.
no, no, that is not necessary because there is a connected. This is already a tree.
Yes, 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 yes. Yeah.
So there is connectivity between each of the terminals. There is connectivity between D and each of the terminals as well. So we have ensured that we have a tree where K1, K2, K3 as well as D are connected among themselves. So now we can take the sum of these weights on the edges that we have taken. This sums to 5 ones and 1 2. That is 5 plus 2. So that is 7. So we know that this answer should be 7. Okay.
Yes, yes.
So now we have to do this business of breaking this D into two parts and so on. That will take some time. So at this point, we can take a break and we can come back again. So the remaining two questions will not take more than 15 minutes. That is my feeling. So even now, if we finish, so let us come back around 6:50.
Sure, sure.
So welcome back. Uh, so we are interested in computing this entry, which corresponds to the minimum possible weight STEINER tree for K1, K2, K3, and T. So we have already seen visually that such a STEINER tree will have weight 7 because this is a realization. But if we use this partitioning of the terminals and then pairing it with all possible non-terminals, then we will get this recurrence. And in this recurrence, we'll have so many possible uh, cases to consider. So this is corresponding to partitioning K1, K2, K3 into K1 and K2, K3. So all these four are corresponding to that. So A, B, C, D are different non-terminals. So these entries are already calculated in the table. Similarly, this is corresponding to partitioning K1, K2, K3 into K2 and K1, K3. And this is corresponding to partitioning K1, K2, K3 into K3 and K1 and K2. So is this recurrence understood?
Yes, yes, and there would be, finitely many, or there would be polynomial number of such equations to be solved, and moreover, all these entries are available there in the table.
Yes, there are 4 plus 4 plus 4, 12 entries. So you have to check all these 12 entries. You have to find the distances also, and it will come out to be 7. So that will require some more work. I mean, I don't want to uh, do the verification now, but you can verify for yourself that the minimum out of these 12 entries is corresponding to 7. That you can look it up from the table.
Yes, I'll do it on my own. Yeah.
Okay, thank you. So now we have two more questions, and these are like very simple. So this is something, yeah. So I'll talk about it first. So there are certain items. So there's a camera, there is a guitar, there is a mic, there is a book, a notebook, there is a radio, and there is a clock. And these are to be distributed among 5 human beings, right? So every human being, every person has some preferences. So for example, person one prefers to be given the camera, the mic, the radio, and the clock. And if the guitar is given to person one, then he finds it useless. So that's why utility of giving this item 2 to person 1 is set to 0. And the utility of giving this item 4 to person 1 is also 0. That means this person doesn't like the notebook. He has 0 value for the notebook and so on. So this matrix is corresponding to the likes and preferences of the persons towards these items. Okay. So the problem of finding non-wasteful NV-free allocations for items with binary utilities, as discussed in this lecture, we formulate an ILP for this instance shown below. So let's look at the ILP. So is it very bloody?
No, no, I can see it. I can see it. Only thing is that, yeah, some of the terms, in this table, their meaning is not well understood.
Which one is not understood?
So like say the entries are binary here. So what's the meaning of one here? That the person one likes the item one, or
Yes.
okay, okay.
One
And
means, yeah.
yes, yes. Please go ahead. Yeah.
Yes, yes, yes. Utility one means this item is valued positively by this person. Utility zero means this person is not valued by this person.
Okay, okay. And some constraints are given below, probably.
Yeah, so these items have to be distributed. So there are 6 items. So they have to be distributed to these 5 people so that uh, everything is distributed and no person.
Your video got freezed, and your video and audio got freezed.
Okay.
No, I could not hear you. Your video and audio both got freezed. Sorry.
I don't know what is the issue. Can you try relogging?
Yes, I can try.
Yes, can you hear me or see me now?
Yes, yes, I can hear
All right, all right. So you can also see the screen.
you. Yes, yes, visible.
So these items have to be allocated to these people so that everybody is happy. So happy means envy free. So nobody should think that the other person's allocation is better than his own allocation. So that is the objective. So to that do that there is an ILP formulation, and then you can solve the ILP, and there are certain FPT algorithms for that ILP. So that will give you some allocation uh, where NV can be sort of minimized. But the question here is okay. So before going to the question, so let's first understand uh, how we shall categorize these items. Before we distribute the items, we have to sort of judge the utilities of the items with respect to the persons. So, for example, consider this item camera, the mic, and this radio. So, these three items can be grouped together on the basis that person 1, person 3, and person 5 value these three items positively. So the point is this item, and this item can be thought of as equivalent with respect to person 1, person 3, and person 5. So that means it doesn't matter whether you give the camera to person 1, person 3, or person 5. Uh, I mean, these three items can be given in any order to these three persons without causing an issue of envy. Is that what I'm not able to hear you? So shall I repeat what I said?
Yes, am I audible now?
Yes, now I can hear you.
Okay. Yeah. And so how many item one, item three, and item fives are there? Unlimited, or do we have the limited number, limited quantity of these items?
So there are there's some echo.
Oh, I see. So yeah. So I mean, so do we have these items unlimited, or do we have the fixed quantity of these items?
We have exactly one item of each.
Oh, so how? So, okay, okay. So how is that possible? Then the item one has been given to the person one, person three, and person five altogether.
Yeah, I mean, I'm saying that so these three items for let's take one item at a time. So this is the camera. This is
Yeah.
valued positively by three people. Person one, person 3 and person 5. Okay.
Yes.
So now if you give the camera to one of these 3 persons, then the other 2 persons will be jealous because the other two persons will be empty-handed.
Yes. Yes.
On the other hand, this item 3 is also liked by this same set of people.
Mhm.
This item 5 is also liked by the same set of people. So if you give one item each to these 3 persons, then everybody will think that I have received an item of the same or more value than what the other person has received, because they value these 3 items equally.
Yes.
So they cannot distinguish between the value of a radio and a camera. So camera and mic and radio are equally valued. So these 3 items can be given in any order to these 3 persons.
Yes,
So
but yeah, that's true. But I mean, we have only one item one and then one item three and so
yes,
on.
yes, 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 that is true. But the person getting the camera will be equally happy if he gets a mic. So it doesn't really matter what he gets as long as he gets one of these 3 items.
Okay. Okay.
So we can ensure envy freeness among these 3 persons if we distribute one item each out of these 3 items. So that is what is
Yes.
written here, that each of these 3 items has the same fingerprint. Fingerprint means the set of persons having preference for an item. So this item is preferred by these 3 human beings. So therefore, we are just using a term and saying that this item has a fingerprint of this. And similarly, this guitar is loved by these 3 people. So there's a fingerprint. A guitar's fingerprint is these 3. Notebook's fingerprint is also person 2, person 3, and person 4. So far so good. We are left with one more item. So for every item, we have sort of uh, defined what is called a fingerprint. Okay. Now it
Yes.
comes to allocation. So now we have to check whether this allocation is NV free or not. Or anyway, so first of all, what are these variables? So I'll enlarge it. So they define an integer linear programming. So in this integer linear programming, they use these variables. So the variables are corresponding to the persons and the fingerprints. So the subscript is corresponding to the person and the superscript is corresponding to the fingerprint. So this says, so this variable x sub person I super person ijk implies means that this person 1 receives an item of this fingerprint or not. So this variable is set to 1. That means an allocation is made from this pool of this fingerprint person 135 has this pool of items. So one of the items from this pool has been allocated to person 1, but person 2 has not received an item from this pool. Person 3 again receives one such item from this pool. Person 4 doesn't receive it. Person 5 receives one item. But which item is not explicit from this uh, equations? Person 1 gets which of these 3 items is not explicit. Person 3 gets one of the items, but which of these 3 is not explicit, and same is for person 5. All right.
Yes. Yes.
So similarly, Again, from this pool 2, this is a pool of items with fingerprint 2. Person 2 receives one item and person 4 receives one item. That is the meaning of this set of equations. And this set of equations says that from the third pool of items, that is the clock is given to person 1. Okay, fine. So now this is an envy-free thing. That is a different issue. But the question is not that. Oh, the question is not written here. Let's look at the question. So this is a question. So it can be verified that the following assignment of ILP variable satisfies all constraints. So how many allocations correspond to this assignment? So the question is, in how many ways you can distribute the items according to these set of equations, so that NP freeness is anyway assumed. The question is how many. I'll just write this thing. How many allocations correspond to this assignment? 9, 10, 11, and 12 are the options.
So we can solve this ILP. Uh,
Yes.
what filter is, yeah, the screen is visible now. So yes. So like if I, so the number of the constraints here are
Yeah, there are the constraints are not even given to you, only the allocation. So somebody has said that, look, I can give you this set of assignments. So person 1 is
mhm,
getting one of the items from pool 1. This is pool
mhm,
1. Person 1 gets one of these items. Person 2 doesn't get anything. Person 3 and so on. So this is just saying that, okay, I have 6 items. I have ensured that 6 items are allocated to these 5 persons governed by these equations. Now, these equations are not specifying that which one gets what item. The question is, in how many ways these 6 items could have been allocated to these 5 persons such that these equations were satisfied.
yes. So like say the item 1 can be distributed in 3 ways,
Yes,
and
yes,
the
yes.
same is true for the item 3 and then the item 5. But then if once the item 1 has been distributed in 3 ways, then the item 3 can be distributed in 2 ways only. And
That is
then
true.
the item 1 can be distributed in one more way. So therefore, in six number of the ways, I mean,
Mm.
the first three items can be distributed.
That
And
is true.
yeah, and similarly, the second item can be distributed in 3 ways, and item 2 can be distributed in 2 ways. So 6 ways, six more, 6 plus 6, 12. And item 6 can be distributed in one way only. So 12 plus 1, 13. 13 number of the ways, I guess.
So is it going to be addition or multiplication?
I mean, once so each item, I mean, once I gave these items, yes, so one set has been assigned, and uh, and for the second one, I mean, there won't be any effect of the first allocation over the second one.
Yes, there
So
is independence is there. Yes.
dependency is there. So if this is the case of the independence, so then yeah, so this would be the product rule will come into the picture, I guess.
Yes,
So
yes.
6 into 6, 36 into 1, 36 number of them.
Okay. So yes, so it is just one thing you have everything is fine. So it is, you have said 6 into 6, but it is not 6 into 6, it is 6 into something else. So let us see what is 6 into something else. So these two items have to go to these three. Okay. So
Yes.
now, so first, wait. Yeah. So first, let's see. These three items have to go to these three guys. So for the first item, you had three choices. For the second item, you had left with two. For the third item, you have only one. So 3 into 2, there are 6 ways you can distribute these three among these three. That is fine. All right. Now these two have to go to two persons, not to three persons. So they are saying that, okay, person 2 and person 4 are chosen. So one person is not, 3 is not getting anything. This guy is not getting, this girl is not getting anything. So person 2 and person 4 are getting one of these items. So you have to choose between person 1 and person 4 for allocating this guitar. So there are two ways. Now, once you have made that choice, then for the notebook, you are left with only one way. So there are two ways of allocating these two things to these two persons. And six
Oh,
you already had before.
yeah. So I think probably then there is some error in this figure because the person 3 is listed here and it is not given there in the constraints below. Because I assume that whatever is given in this figure, I mean, these in fact are the constraints and have been translated into the variables below. Uh, yeah.
No.
Or
So
is there any
the
reason that the person 3 cannot be allocated because the person 3 has already become happy and after getting one of the three items, or is there any other reason?
correct. So person three has already got something. Uh, Person one has already got something. Person five has already got something. So definitely in the next iteration, we have to prioritize person two and person four. And this clock is not valued anything by anybody. So even if person one gets a clock additionally after getting something in the first round, nobody is bothered. Nobody is envious.
Yes.
Because if you look, this clock is only valued positively by person one. Nobody is bothered whether the clock goes to the person one or not. So that was the issue. Otherwise, you are right. So 6 ways of allocating these three to them, and 2 ways of allocating these two to two of them, and 1 way of allocating this to this way. So these things are independent events. So there are 12 ways to sort of allocate these items NP freely according to this allocation
Yes.
assignment. Sorry. So this is 12. This is the answer.
Yes.
So the constants are not given. This it's an ILP, but the constant is something that you have to look up from the book or from the video. It's very nice. The set of constants are quite complicated. I think that's why they didn't bother to describe the question in terms of the constraints. It's not straightforward. Okay, so let's go to the last one for today. Where is the last question? Last question is very simple. Uh, okay, so this requires 5 minutes. This requires maybe 2-3 minutes of setting up. So let me set it up for you. What is the question? So you are given a graph. Uh, Picture is not here. Oh, ho, ho, ho. Sorry, picture has to be copied. So you are given a graph, and additionally, you are given in this graph a vertex cover. So now there is an ILP for what is called the imbalance problem on the graph with respect to the vertex cover. So the vertex cover size is the parameter in the imbalance problem. So the graph is the input and the parameter is the size of the vertex cover. And then we formulate an ILP to solve the imbalance problem. So we'll just set it up for you. So here is a graph. So you can see that in this graph, these three vertices H, E, and S, they form a vertex cover. What is a vertex cover?
So the minimum set of the vertices covering all the edges of the graph.
Yeah, so the minimum set of vertices such that all the edges are covered. Although the name is vertex cover, but the covering is happening for the edges.
Yes. Yes.
Okay. So now, what is the imbalance? So let me first define what is the imbalance question. What is the imbalance problem? So I'll give a simpler example. So here is a simpler graph ABC. So the objective in the imbalance problem is to find an ordering of the vertices in the graph such that uh, imbalance with respect to the ordering is minimized. Okay. So so let us say one ordering is A, B, C. So this is one ordering. Okay. So imbalance of vertex A with respect to this ordering is how many vertices, how many neighbors. So neighboring vertices of A to the right minus the neighboring vertices of A to the left. So I will write this way. So neighbors of A to the right in the ordering pi minus neighbors of A to the left in pi. So now I will describe what it means. So A has only one neighbor, and in the ordering, this one neighbor B is to the right. So this number is 1. And A doesn't have any other neighbors, so there are no neighbors to the left. So this number is 0. So this is 1 minus 0. So the imbalance of A is 1. Okay. So I'll write it down. So imbalance of A is 1. So now if you understood what I said, what is the imbalance of B?
So imbalance of B is 0. Ah, 0. So yeah, it is 0.
Yes. So B has two neighbors, A and C, and in the ordering A is to the left and C is to the right. So 1 minus 1 is 0. So what is the imbalance of C?
So I guess that whenever the degree of a vertex is even, then the value of the imbalance thing is 0. And if the degree of a vertex is odd, then the value of the imbalance thing would be equals to 1.
In this ordering, yes. In this ordering, not in the other ordering. So in, for example, you could have another ordering like B, comma A, comma C. So with respect to that ordering, what will be the imbalance of? So you what did you say? Imbalance of uh, uh, even indexed is 0. That's what you said.
Yes, yes. So imbalance value of a vertex whose degree is even would be equals to 0. I mean the value of the imbalance thing would be a Boolean value. Either it would be a 0 or a 1.
No, that is not true. For example, in this case, imbalance of C is 1 minus 0. But let us say the ordering was BAC. Then what is the imbalance of A?
So if it is A, then B to A and then A to C. So imbalance would be equals to B to A to C would be equals to 0. Right, so the degree of A is even.
No, so degree of A is the graph is this only. That this is the pi. This is the ordering. So this is a different ordering.
Oh, I see. I see. Okay. So ordering means what? So I mean, while considering this ordering, then oh, I see. I see. But then how can I mean, traverse from B to A and A to C because there does not exist an edge in between A to C.
What do you mean by traversing?
So for an ordering, at least the path should be traversable, isn't it?
No, ordering means it's just what comes after what, that information, that how are we going to look. It is not about traversing in the graph. It is about how we are going to call out names. So this is saying that I'm going to look A first, then B, then C. So A is followed by B, followed by C. This is saying that B is followed by A, followed by C. This is just a ordering. It's sort of like how you are throwing things.
Okay.
So now with respect to this ordering, if you see, A has only one neighbor, B, and B is to the left. So this value is 1, this value is 0. So 0 and minus 1, this is 1. But on the other hand, what is the imbalance of B? So B has two neighbors. Both the neighbors are to the right. So that imbalance is 2. Imbalance of C is one neighbor is to the left, so that's 1. So the total imbalance with respect to this ordering is the sum of these imbalances, that is 1 plus 2 plus 1, that is 4. Whereas the total imbalance with respect to this ordering is only 1 plus 0 plus 1, that is 2. So we want to find that ordering where imbalance is minimized. Is that understood?
Yes, yes.
So it depends on what is the order. So how many possible orderings are there for n vertices? N factorial. So now in this
Mhm.
graph, there were three factorials, that is 6 possible orderings, and then with all the 6 factorial orderings, you have to check that which one minimizes the total imbalance, and then that is your answer. So far so good. This is the graph, and in this graph, you know that this is the set of vertex cover. I mean, this is a vertex cover, HES. So we can spend a minute to see that this is in fact a vertex cover. None of the edges are left out after you have taken these 3 vertices.
Yes, yes. I mean, H, E, and S are the. This indeed is
Okay,
the word.
okay. So now, huh. So now you can read the question. Now we are in business. Okay, so what is type also I have to tell. So look at each vertex in the vertex cover. Let's say H. H is responsible for so what is it? Okay, so H is connected to all these things, but that is not the point. The point is okay, so yeah, you have to look the rest of the vertices. All right. So for the rest of the vertices which are outside of the vertex cover, check that the rest of the vertices, each of them are connected to which subset of the vertex cover. For example, G is connected only to H and nobody else in the vertex cover. Similarly, A is also connected to only H. Therefore, A and H are of type, sorry, A and G are of type H. That is the definition of type. Similarly, F is connected to both B and H, and B is also connected to both B and E and H uh, in the vertex cover. F is connected to H and E. B is also connected to H and E. So B and F are of type HE, and C and P are connected to all the vertices in the vertex cover. C is connected to all three, and P is also connected to all three. Therefore, C and P are of type HES. D is connected to E alone, so D is of type E, and Q and R are connected to S alone, so Q and R are of type S. Okay, so the type definition is clear.
Yes, yes. Types.
Okay, so now you have to find an ordering of these all these vertices such that imbalance with respect to this ordering is minimized. To do that, first what you do is you fix an ordering of the vertex cover vertices. So there are 3 vertex cover vertices. There could have been possibly 3 factorial orderings of this vertex cover vertices. So you fix one ordering HSC. So H you are going to see before S, I mean, H is going to be followed by S in the ordering, final ordering, and S is going to be followed by E. That's what your assumption is. And the remaining vertices, which are outside of the vertex cover, you are going to put in these gaps. That is going to give you the final ordering for the full set of vertices. So for the remaining vertices, you have so many gaps or locations where you can place them. All right.
Yes, yes, yes.
So now this is the question, that how many gaps are there? 4. So that is the vertex cover size plus 1. That's what they're saying, that there are so many gaps or locations. Now, if you place, now the question is, the imbalance of a vertex of type T, if it is placed at a location, oh, what happened? Oops, just a second. Sorry. Okay, now the question is visible. So we want to find the value of this thing, Z HES 2. So what is the meaning of this? This is the meaning of the imbalance of a vertex of type HES if it is placed in the gap or location, I'll just say location 2. Okay, so what is location 2? This part. So you are going to place a vertex which is of type HES, that is either C or P here. So let us I put C here. So what will happen? You know that this is connected to HES all 3. So how many neighbors are to the left? So if you in your final ordering, if you put C here, you know for a fact that H is here, S is here, and E is here. So how many of these 3 neighbors are to the left of C?
Yes, so left of C is 1H, and then right of C would be S only, because I would be requiring one more thing in between S and B.
That is fine. So whatever is to the right of C, out of them, how many are neighbors? So S and E are definitely neighbors of C. That is the reason C is of type HES. So C is of type HES. That means HES, all 3 are connected to C. So
Yes.
C has at least 2 neighbors on the right and this one neighbor on the left. So the imbalance is 2 minus 1. That is 1.
Yes.
So we'll look at the answer. Uh, the answer is 1. So this is basically just sort of, counting that how many neighbors are to the left and how many neighbors are to the right. And you take the difference, that is going to give you the imbalance as far as this problem is concerned. But more interesting is how to sort of look at this figure. More interesting question is, given such a complicated graph where so many permutations are possible, what is the correct permutation you should take so that imbalance is minimized? For that, there is this nice ILP formulation which leads to this FPT algorithm. That means running time is sort of 2 to the power the size of the vertex set, and with this much running time into some polyfactors, you are able to find this balanced partition ordering. The imbalance is minimized. So that is more interesting. But yeah, I mean, so you can look it up from the book. It's already 2 hours. I could not finish it in uh, 1.5 hours today.
Yes,
So
yes. 8 hours, yeah.
yeah, it took more time than what I expected. So anyway, thank you for coming. Thank you for coming early at 5:30. So I will see you next time.
Thank you so much. Bye bye.
Bye.